Good morning, guys. I'm going to step out of the way real quick and let you get this stuff copied down. We're going to start talking about rational functions or graphs of rational functions today. But I want you to get all of this stuff down real quick. So I'll talk as you write. First thing we can see here is holes. Now we've looked at simplifying rational functions before, setting them factoring numerators, factoring denominators, and then canceling any factor that occurs in both the numerator and denominator. Well, graphically speaking, what happens when we do that is we get what's called a hole in the graph. It doesn't show up for that particular area, but the function is undefined at that. So it's a value that, because it's a restriction on our domain, as we've looked at before, because it was showed up in the in the denominator as a 0, it's going to show up in the graph as an undefined portion of our graph. So it's a hole in the graph. So to get holes, we just take any canceled factors and set them equal to 0 and solve. Y-intercepts the same way we've always found y-intercepts. Just evaluate the function at x equals 0, so plug in x equals 0. X-intercepts, think about what makes a fraction equal to 0, because we know that x-intercepts occur where the function equals 0. So just look at what makes a fraction equal 0. Well, the numerator's got to be equal to 0. So we take our simplified numerator, because we've already pulled out all of the holes. That's the zeros that occurred for both numerator and denominator. So we're going to look at just the x-intercepts. So we look at the simplified numerator and set it equal to 0 and go through and solve. Next, we're going to look at vertical asymptotes. Now, these are very similar to the asymptotes that we talked about when we did our logarithmic functions. So vertical asymptotes are that vertical line that we approach, that our function approaches but never actually gets to. We can't equal that value because our function is undefined at that value. So to get that, well, what makes a fraction undefined? Well, the denominator being equal to 0 is where we're undefined, as we saw with our restrictions early on when we were simplifying our rational functions. So to get vertical asymptotes, we're going to set the simplified denominator equal to 0. So it's pretty straightforward. Holes are the canceled factor equal to 0. X-intercept is simplified numerator equal to 0. Vertical asymptote is simplified denominator equal to 0. And the y-intercept is what we get when we plug in 0. Now, horizontal asymptotes are a little more involved in that we're not just simply setting something to equal 0. Horizontal asymptotes is, as we get out, as our domain approaches positive or negative infinity, our rational function is going to level off. It's going to tend towards some line. So that's what horizontal asymptotes are. They're the horizontal line that our function tends toward as we approach both positive and negative infinity, once we're plugging in very, very big x values. So it comes down to relating our degree of our functions. So degree of the numerator as it relates to the degree of the denominator. And just think of what's going on. The degree tells us how fast our numerator or denominator are growing. So if the degree of the numerator is greater than the degree of the denominator, meaning as I get out towards positive infinity or negative infinity, the numerator's got a bigger exponent on it, then there is no place where that line's going to level off. Because if my numerator's growing so much faster than my denominator, because it has that higher exponent, what we see is it starts to look like a polynomial. So, because the denominator becomes so small and irrelevant, we're left with almost the numerator. So what we end up with is there is no horizontal asymptote. Instead, we get what we call an oblique asymptote. And I'll talk more about oblique asymptotes in a minute. But an oblique asymptote is not a horizontal line that our graph tends towards. It's we can have a slant asymptote. We can have a quadratic asymptote. It's just some type of curve that we don't see that the line, that the rational function happens to follow along as we go towards positive or negative infinity. And again, we'll look at some examples of those in a minute. The next relationship is, instead of the degree of the numerator being bigger, is if the degree of the numerator and denominator are the same. So say I have an x squared function over an x squared function, or an x to the 10th function over x to the 10th function. Well, what's happening in that case as we go towards positive and negative infinity is that the degrees cancel each other out for the most part. X squared over the long term, when you're talking about a million squared over a million squared, or 10 billion squared over 10 billion squared, what we're going to see is that the exponent parts become irrelevant, and all we're left with is the coefficients on those exponent, on those large degrees. So we end up getting this horizontal line, horizontal asymptote, of y equals a over b, where a is the lead coefficient of the numerator and b is the lead coefficient of the denominator. And it's because those degrees were the same. As we get towards positive and negative infinity, all that little stuff, the little extra adds on, if we're talking about quadratics, the linear and constant terms don't matter towards positive infinity, and the x squared, the lead terms, take over the function as we get towards those very, very big values. So really it's just whatever we're multiplying by those that determine where the function is going to level off or tend towards. So again, if numerator is equal to denominator as far as degree is concerned, it's just the lead coefficient of numerator divided by lead coefficient of denominator. And then finally, we can either be bigger on top, we can be the same, or we can be bigger on bottom. So if the degree of the numerator is less than the degree of the denominator, that means the denominator is getting so much bigger, so much faster than the numerator, we get in essence 0 as we get towards positive infinity, because you're going to have a very, very tiny numerator, and towards negative infinity rather, you're going to have a very, very tiny numerator compared to an enormous denominator. So think of it as if I had 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 1 over 64. As I get bigger and bigger and bigger with my denominator, I get closer and closer and closer to 0. So y equals 0. Now a couple of comments on if we were looking at the actual graphs. A vertical asymptote is a line we cannot equal. Our function is undefined at that point. So we can never equal a vertical asymptote. Our graph can never cross a vertical asymptote. A horizontal asymptote is a trend as we get out towards positive or negative infinity. So it just tells us what our graph is looking like out on the ends, and not necessarily where we can and can't equal those values. So we can cross horizontal or oblique asymptotes. We just trend towards those or level off on those lines as we get towards positive and negative infinity. But a vertical asymptote can never, ever, ever be crossed, because again, the function is undefined at those portions. Okay, so that's just the terminology, the definitions for each of these components to a rational graph of a rational function. Give me a second, I'll get some examples up here, and we'll look at numerically what's going on with each of these concepts. So here I have a couple of examples for you. We're going to start by identifying the key features, and then we're going to show you how to put it all together in a graph. So first thing we do with any rational function is simplify the rational function. So we factor our numerator, x plus 2, x plus 1 for the numerator. Factor our denominator. We would do factor by grouping on this one. So pull out x squared, pull out minus 4. And you're going to be left with 2x plus 1, but x squared minus 4 can break down again into x plus 2 and x minus 2. If you need to review your factor by grouping stuff, just go back to your factoring higher degree polynomials lecture, and it'll go through all that stuff again. Then we cancel what can cancel, so the x plus 2's, and we know those are where our holes occur. So x plus 2 equals 0, subtract the 2, so x equals negative 2. So then y-intercept. Y-intercept is what we get when we plug in 0. So if I plug 0 into my function, I can plug it into either part. It doesn't make a difference. 0 squared, 3 times 0 plus 2, 2 times 0 cubed, 0 squared minus 8 times 0 minus 4. Now remember, y-intercepts, if we think back to where we did quadratics and where we think back to where we did our polynomial functions, y-intercepts were always the constant. Well, they're the constant because they don't have a variable in there to make them equal 0, to multiply them by 0. So if you want to think in terms of rational functions, it's still going to be the constants, but it's a ratio of your constants, because you got two little polynomials you're looking off of. So our y-intercept is at 0 and negative a half. So we don't always have to plug in 0 if you'll understand that concept of ratio of constants. X-intercepts are where the simplified numerator equals 0 So x plus 1 equals 0, subtract 1, x equals negative 1. Vertical asymptotes are the simplified denominator. 2x plus 1 equals 0, subtract 1, divide by 2, x is negative a half. X minus 2 equals 0, add 2, x equals 2. And then finally your horizontal asymptote. So we look at our original expression, and we could do it here, but we'd have to put it back together, so might as well look at it right here. And we're comparing degrees. The degree of the denominator is greater than the degree of the numerator. So we can say bigger on bottom. Get very mathematical and scientific right there. We have a bigger exponent on bottom. So that tells us, if we look back to our rules, that the horizontal asymptote should be y equals 0. The reason is because as we get towards positive and negative infinity, this is going to get closer to infinity. This is going to get to infinity faster than this is. So that's going to become so great that it makes the numerator completely irrelevant. So we have a huge number divided into a tiny number, which in essence becomes 0. So bigger on bottom, y equals 0. Now let's look at how to put all this together on a graph. Well, most of it's just plotting your points. So as we go through, holes we always do last because they're not actually going to be an intercept or a line. They're going to show up in the actual curve. So let's start with our y-intercept, which is negative a half. Let's start with then do our x-intercept, which is at negative 1. Vertical asymptotes are at negative a half and positive 2. Horizontal asymptote, y equals 0. We'll pretend that was a straight line. Now we're ready to graph. Now there's two things that you need to remember or understand to be able to put all this information together and give us a curve. First is you can only cross the x-axis at x-intercepts. Only cross the x-axis at x-intercepts. And the second is, how do we approach asymptotes? Well, the approach of asymptotes is either going to be the opposite, meaning if I'm going to the top of this one, I'm going to come out from the bottom of this one, or they're going to be the same. If I go in through the top of this one, I'm going to come out of the top of that one. What determines that is the multiplicity of that asymptote. Think back just like we did when we did our polynomial functions. If we had an odd multiplicity, we passed through that point passed through that x-intercept, and when we had an even multiplicity, we bounced off of it. So we just turned right around. It's going to be the same thing with these asymptotes. If I have an odd multiplicity, if I'm approaching from one direction, I'll come the other direction out of it. Okay, so I'll be pointing up on one side and down on the other side. If it's an even multiplicity, that would be the same. So say this had an even multiplicity, we would go up, approaching it, and we would be decreasing coming out of it. So it'd be pointing up on one side and pointing up on the other side. So you'd get them on the same sides of the x-axis for that particular thing. So evens are going to be together, odd multiplicities are going to be apart. So that's how, if we know those two things, we can put together. So start with your y-intercept. In this interval that has the y-intercept, and there's no x-intercepts, so we know that all of it has to stay below the x-axis. Now remember, you cannot cross vertical asymptotes because these are the points where our function is undefined. Our graph can never equal those, so we can't have any points along those. Now we just use those multiplicity rules. So the negative a half only occurred one time, so since it's down on this end, it's got to be up on this end. Now we'll come on down, got to cross the x-axis, but remember, since this is our horizontal asymptote at 0, it's going to double back up and level off. Now remember, as we've talked before, you can cross horizontal asymptotes. They're not where your function is undefined. Horizontal asymptote gives us the trend as we get out towards positive and negative infinity. So towards negative infinity, this one's going to get closer and closer and closer to equal and 0. So it's going to level off along 0. But we can cross a horizontal asymptote any number of times. On the right-hand side, see how we're pointing down on this? Since the 2 has an odd multiplicity, it only occurred one time, then we've got to be going in the opposite direction on the other side of the asymptote. And the last thing we're going to graph is our hole. Our hole is at -2. So if I go over to -2, the way we graph a hole is to literally take your curve and erase that spot right there. So we have a hole in the graph. And so what that means is it wasn't enough to make it a vertical asymptote because the numerator canceled it out, but we still have to show that it's undefined at that value. And so we just show that there's a little gap. And that's seriously what the graph does. Because remember, a graph is not a continuous line. A graph is infinitely many points thrown out there, and then they demonstrate this curve. So it's not like on your calculator where it starts on the left and then plots every single point from left to right. No, it's just infinitely many points thrown out there all at one time, and we can look and see how they all plot and level out together. Now, this one point, there's just nothing right there. Same as this one point. There was nothing there, there was nothing there. But we actually had points on either side of it that gave us this vertical asymptote. But that is just a gap in the graph. We would say that rational functions here are discontinuous because we can't account for every single point, every single value from -infinity to positive infinity. So because our function starts over at -infinity and ends at positive infinity and is not defined for every point in between, we say it's a discontinuous function. The polynomials we've worked with before, they're continuous because there were no interruptions in that domain. So just a couple of key little words that you'll want to be familiar with: continuous and discontinuous. So that's how you graph all of this information that we get from that expression. I want you to take a couple minutes, pause the video, try to get the key features, the holes, y-intercepts, x-intercepts, vertical asymptotes, and horizontal asymptotes, and put them together in a graph. So pause this, work on that, and I will hang out right here. Okay, hopefully you were able to get a graph. Let's put all this together and see if it matches what you came up with. First thing we're going to do is simplify our rational expression. So we'll factor the numerator, difference of two squares, x plus 1, x minus 1. Factor our denominator. So that's 2x and x. That's going to be minus 3 and plus 1. Right? Negative 3x plus 2x is negative 1x. Cancel the x plus 1, so we know that's our holes. So x plus 1 equals 0, so hole is at -1. Y-intercept is what we get when we plug in 0, so 0, 0, 0 is going to leave us -1 over -3, so it's a ratio of the constants. So 0 and 1/3. X-intercept is simplified numerator equals 0, so x equals positive 1. Vertical asymptote simplified denominator, so 2x minus 3 equals 0, so x equals 3/2. Horizontal asymptote, look at your degrees. Equivalent degrees. Equivalent degrees, so we know that it should be a ratio of the lead coefficients. A ratio of the lead coefficients. So go back to your original function, and it's 1 over 2. So y equals 1/2. Get my arrow straight. Okay. And that's all of it. Let's graph it. So we're going to plot our y-intercept, which is at 1/3. We're going to plot our x-intercept, which is at 1. Vertical asymptote is at 1.5, 3/2. Horizontal asymptote is at 1/2. Now we start with our y-intercept. Okay, we see how the x-intercept is right here next to it. So the only place this one can't go up because it's got to hit this y-intercept or this x-intercept. So it's going to come on down through the x-intercept and then just keep going and level off at your infinity. Your 1/2 as we approach -infinity. Now this 3/2 only occurred one time, so we need to see, since it occurred one time, it's going to come from the opposite direction. So if it comes from top, no x-intercept, so it just levels off right there at the asymptote. Technically, we don't know exactly where it does this. It could dip down below the asymptote and then redirect, but that gives us a good enough idea of what's going on out here towards positive infinity. And then we finish with our hole. Our hole is at -1. So at -1, we go make a hole in the graph. So that is the graph of this rational function. Now I got one more that I want y'all to look at, and it's one where the horizontal asymptote is going to be a little different from what we've done. So let's put that one up here, and we'll go through it together. So for the third one, f of x equals x cubed minus 8 over x squared minus x minus 2. So we'll go real quickly through this one because it's got special x-intercepts, and the asymptote is a little bit different. So let's check it out. First thing we do is factor. So we recognize difference of two cubes, so it's x minus 2 and x squared plus 2x plus 4. For here, for the denominator, x minus 2 and x plus 1, right? Negative 2x plus 1x is negative x. So what canceled? X minus 2's. So there's your holes. So x equals 2. Y-intercept, 0, 0, 0. So we're left with a ratio of the constants, which is going to be -8 over -2, which is, I'll write that in there. -8 over -2, so that's 0, 4. X-intercept is simplified numerator. Now right now, I know that there are no x-intercepts because this right here has to give me two imaginary solutions. Remember when we do a sum or difference of cubes, you're only going to get one real solution. That's going to come from your linear factor. Your quadratic factor is always going to give you two imaginaries. So this one right here has no x-intercepts. If you had forgotten that, you would solve that. You would get your imaginary solutions, and we would say there are none as far as x-intercepts are concerned. Vertical asymptotes, simplified denominator. So x equals -1. Horizontal asymptotes, bigger on top. So if it's bigger on top, if we have a larger degree for the numerator than we do for the denominator, there is no horizontal asymptote. And if there's no horizontal, then we say there's an oblique asymptote. Oblique asymptote is going to be the quotient of the numerator divided by the denominator. If we want to know what's going on as we get towards infinity, we just divide this. It's like reducing a fraction. If this was 6 and this was 5, it would be 1 1/5, right? So it's the same idea. We're going to divide this and see what we're really looking at as we get out towards positive and negative infinity. And what's going to happen is when you divide that, you're going to get some expression, right, with a little bit of a remainder. Maybe not a remainder. Sometimes there's not a remainder. But we're going to divide, and if there's a little bit of a remainder, that remainder is going to be so tiny as you get towards positive and negative infinity, you're going to be left with really just that function, the quotient portion of it, instead of the remainder portion of it. So to get oblique asymptotes, we just take our function, and we can do it here or we can do it here. Okay, it doesn't matter if I'm looking at 12/10 or if I'm looking at 6/5. They're the same thing after we divide. So I just would work right here because it's smaller, easier to work with numbers. You can long division or in synthetic division this. It's your call. I'm going to do long division because I guess I'm a masochist or something. I don't know. Just to remind y'all, I guess, how to do long division. First divided by first is x. Distribute that. X squared plus 1x, subtract, that cancels, leaves us x minus 4, or plus 4, first divided by first. So plus 1, distribute that, x squared plus 1x, nope, x squared plus 1, x plus 1 rather, subtract, cancels, leaves us 3, so plus 3 over x plus 1. Well, for the oblique asymptote, we just want that quotient. So y equals x plus 1 is our oblique asymptote. This is what our graph is going to tend towards as we get towards positive and negative infinity. Because again, it goes back to, see how we have the exponent on the bottom is bigger than the top? So this is going to get 3 over infinity, or 3 over negative infinity, which is almost 0. So as we get to positive and negative infinity, we're going to get this line right here, plus 0. So it's really just that line. Now, how do we put all of this into a graph? Well, let's look at it. To graph all this happiness, just plot like we've always done. Holes we hold on. Y-intercept is 4. So there's 4. X-intercepts, there are none, so we're good there. Vertical asymptote at -1. Was no horizontal, so we had to go to the oblique. The oblique is x plus 1, so go 1, go up 1 over 1. So there's going to be our oblique asymptote. And then just like before, we're going to go through the y-intercept. Now there are no x-intercepts, so we know we can't approach this y from the bottom. It's got to be approached from the top. Okay? And then same rules apply. This -1 occurred only one time. It didn't occur an even number of times. So we've got to work from the other side. So if we're pointing up on this side, we're going to be pointing down on this side. And again, no x-intercepts, so I'm never going to get up to the x-axis. I'm going to get up close to it, and then I'm going to come back on down and follow my oblique asymptote. So this is our line that we're leaning towards and starting to look like as we get towards positive and negative infinity. Real quick, let me show you one that has an even multiplicity, just so y'all can see what I'm talking about as far as pointing in the same direction. So if we had something like this, f of x equals x plus 2 over x plus 1, x plus 1. Something like that. Now, going through, no holes in that one. So the holes are none. The y-intercept would be 2 over 1 times 1, so 0, 2. Remember, 0, 0, 0, so you're left with 2 and 1 times 1. The x-intercept is -2. The asymptote, let's say VA right there. Vertical asymptote is x equals -1, and it's a multiplicity of 2. See how we have x plus 1 show up twice, so -1 shows up twice. Horizontal asymptote, let's call it HA. X plus 2 over x squared plus 2x plus 1. So bigger on bottom, that's y equals 0. So if we were going to put that one together in a graph, graph it all out, y-intercept is at 2, x-intercept is at -2, vertical asymptote is at -1, and we're at 0 right there. Okay, so looking at our y-intercept first, we know this y-intercept, it can't come from the bottom because we don't have any x-intercepts on this side, so it's got to come from the top. Now, because this -1 occurred twice, we're going to have to come from the top on the other side of that asymptote. So we'll come on down, much like we did our second example. First example, one of them. We'll come down, hit that x-intercept, and then we'll redirect and level back off at the horizontal asymptote. So this is what I'm talking about as far as if your vertical asymptote occurs an even number of times, you won't approach from the opposite side, you'll approach from the same side. But it all starts with where's that y-intercept at, and are there x-intercepts next to it or not. That's it for graphs of rational functions. So keep in mind what we're talking about as far as vertical asymptotes are where the simplified denominator equals 0. Horizontal asymptotes, we've got to compare the degree of numerator and denominator. X-intercepts are simplified numerator. Y-intercept, or simplified numerator, equals 0. Y-intercept is where is the ratio of our constants, and the wholes are any factors that canceled. Anything that was an x-intercept, because it was in the numerator, equals 0, and a vertical asymptote, because it was in the denominator, equals 0. It can't be both, so it cancels and causes just a hole in the graph, which is just a gap we literally jump over as we are graphing. That's it for graphs of rational functions, and I will see you in class tomorrow, guys.